All right, so yesterday we saw some results about the VC dimension. We saw that in learning plus minus one valued functions in a minimax setting, this is the right notion of complexity. We looked at some tools that are applicable more generally than just in the minimax setting, these Rademacher averages. But we saw that in that setting where we want to be able to deal with the worst case distribution and perform almost as well as a function from some class, then it's the VC dimension of that class that's the right way to measure the complexity of the class. Well, thank you. All right, so what I want to look at today, at least at first, is how we can come up with estimates of the VC dimension. We saw one result for linear threshold functions, that the VC dimension for that class is the same as the number of parameters. We'll see a more general family of results that for linearly function classes parameterized by real numbers that can be computed in a simple way, in some sense. The VC dimension again grows linearly with the number of parameters. But it turns out that for many problems, viewing the functions that come out as our estimates as discrete, as plus minus one valued functions, is not the right way to view them. And we'll see in the second part, actually for the latter 2/3 of the two lectures today, we'll look at large margin classifiers where the algorithms work by minimizing some smooth criterion. That's closer to a regression problem, and then in that setting, it turns out that the VC dimension is not the right quantity. So they're the two parts that we'll be looking at today. The first and shorter part is looking at estimates of the VC dimension for thresholded real valued functions that are expressed in terms of some number of real parameters. I want to start by pointing out some difficulties in estimating the VC dimension for such classes that your first intuitions about the way the VC dimension might scale are not correct. And then we'll look at a general approach to estimating the VC dimension that works, in this case of parameterized functions, by looking at connected components in the parameter space. And we'll see there's this very elegant result giving bounds on the VC dimension for these parameterized classes in terms of the computation time, the amount of computation that's involved to come up with the value of a function in the class. Okay, so I want to start with a few, I guess these are kind of straw man conjectures about how this notion of complexity works for a parameterized class of thresholded real valued functions. So let's think of this general case. We have some function f that takes two arguments, right? This is a real valued function and it takes an argument x, that's in our domain, and it takes an argument theta, which is a d-dimensional parameter vector. Right, and then we're thresholding the value of f and using that as our plus minus one valued function. Okay, so we can just define sign at 0 in an arbitrary way. Okay, so for such a class of functions, we've seen that if f here is linear in the parameter vector theta, then the VC dimension is precisely d, the number of parameters. Okay. So it seems reasonable that in some general case, perhaps the VC dimension depends on the number of parameters. Well, that's obviously not true. You can come up with really complex functions here where, as you adjust these parameters, you sweep out an enormous space of functions. But perhaps if f is smooth or somehow well behaved in terms of the parameters, you might think that were true. Well, there are some simple counterexamples. Here's a one parameterized family, right? It's analytic in the parameters. happens to be analytic in theta as well, in x as well. So we just take the sinusoid function of theta times x. So our domain here is x, and we're considering all real value parameters. It turns out this has infinite VC dimension. All right, and what's going on here is that we can extract all the bits of we can extract information about theta down to any fine level we like just by choosing x sufficiently large. Okay, so the proof here works. We take our xi's as points that go out exponentially far, 2 to the 1, 2 to the 2, and so on. And then for any pattern of bits we want, if we have k of these values, for any pattern of bits, I guess I've written that as 0 or 1, right? We choose our parameter vector to be pi times the real number that has this binary representation, I guess written this way. Okay? And then when we multiply pi times 2 to the something, right, we're just extracting the appropriate bit from this thing. So, the point is, even though we've got some nice smooth function, right, it's moving around a lot, right? As the sinusoid has arbitrarily many wiggles, and we're exploiting those so that we can extract all of these bits from our parameter vector. Okay, and this means that the sign of the sinusoid evaluated at that point has whatever sign we desire at that has whatever value we desire at that index. And this is true for any k. So we can come up with an arbitrary dichotomy of these k points. So since this is true for any k, the VC dimension is infinite. Okay, so smoothness isn't going to help us. There are many other properties that we might assume, but what I'd like to get a handle on is, what are some sufficient conditions for parameterized function classes to have a reasonably small VC dimension. So here's another example, and this is the real valued class we're considering here is a feed-forward neural network. Okay, we have a scalar nonlinearity, linear parameters that enter, nonlinear parameters that enter here, and some linear parameters. Okay, and then we're thresholding this parameterized real-valued function. So we might ask, well, for what scalar nonlinearities can we get a finite VC dimension? We've seen in the sinusoid case, we could put a sinusoid in here and have k equal to 1, and we don't have, smoothness isn't enough for us, right? But the sinusoid has lots of wiggles. What if we make this thing, monotone increasing, right? So it's something like an approximation to a threshold function that we have there. And it turns out through a counting argument, if you put a threshold function in as this function sigma, then you do get a bound on the VC dimension that grows like the number of parameters. Well, it's like d log d if d is the number of parameters in that case. Okay, so some smooth approximation of that seems reasonable that you would get some sensible bound. And we could add all sorts of extra constraints. And I've extended this list. It turns out you can come up with a counterexample that satisfies all of these conditions and yet has infinite VC dimension. And I'm not going to go into the details of it. Right? It goes between 0 and 1. It's monotone increasing, infinitely differentiable. It's concave to the left of 0, convex to the right of 0. So very well behaved function. But with this function, you can take a combination of just 3 of these terms, so two nonlinearities, and get infinite VC dimension. And the trick is you're hiding the sinusoid inside this little function, right? This scalar nonlinearity. So then you can subtract 2 pieces out that have these nice smooth properties, and I think I've got a picture here, right? Here's the difference between the standard sigmoid and the dotted line is this one that's hiding a sinusoid in there. When you take a difference between 2 of these things, you can extract the sinusoid. Okay, it's a very at a very small level, but we're thresholding, so The magnitude of this thing doesn't matter. So we have, through this sinusoid, we have an infinite VC dimension. Okay, so I guess I should step back. This might be some cause for concern, right? That about the theory that here we're talking about the VC dimension. It's the right notion of complexity if you're working in a minimax setting, and yet, when you look at this picture, if we were to do some sort of a gradient descent optimization of a quadratic criterion using a class of functions defined in terms of this thing, right? We're never going to be able to see those small wiggles, right? It seems quite unreasonable. And so the distribution that exhibits the difficulties with the infinite VC dimension is one that is exploiting those small wiggles, okay, in the thresholded class. Point is, the optimization problem that we'd want to solve, that is to find the function from this class, right, that minimizes the empirical error of the thresholded function, that's a very difficult optimization problem, right? And so, this is not a practical cause for concern for this class of functions, right? Because we can't solve the computational problem for this class to minimize the empirical error. So we'll see later when we look in the large margin setting and we optimize a different criterion. We're not minimizing empirical risk. We're not trying to minimize the number of mistakes we make when we threshold our functions. We're optimizing some smooth criterion involving the real valued function little f here itself. Okay, so in that setting, our optimization is not able to exploit the full power of this thresholded class. Okay, we're working with a slightly different criterion, and these kinds of negative results point out, that if we were to work with the right criterion, we'd be in trouble. We'll see later that when we work with something that's not quite the right criterion, we get around this kind of difficulty. Okay, but we'll see also that the general results I'm about to tell you, about to show you these results about parameterized real-valued functions are useful in that setting also. We can build up estimates of the Rademacher averages, for instance, for complex classes in terms of VC dimension estimates for simple classes. So, these results are important even in the large margin setting. Okay, so let me tell you, I need one technical definition to explain the result that we're going to look at for these thresholded real-valued classes. And here I'm just broadening things a little bit to include not just a single real-valued function. My parameters now are I've called them A instead of theta. Not just a single real-valued function, but we've got k of them, and we're combining them in some fixed way with a Boolean function. Okay, so there's no, it's just I want to make my class of functions a little richer, in particular, so that we can include a certain model of real-valued computation and relate the VC dimension to the computational complexity of calculating the value of a function. Okay, so I need this extension to do that. So let's look at the definition. We've got some class G of real-valued functions, right? And all of these functions that we're going to consider are continuous in their parameters, theta or A. And we've got some class of Boolean function. We've got some Boolean function G, right? So this is a thing that maps from plus or minus 1 to the k. Okay, k of these signs are to plus or minus 1. And then we compute a function in our class by first computing these k distinct functions, parameterized functions, and then take some fixed Boolean function of them. All right, so why am I going to this generality? Let's look at, I guess, the stereotypical example. We'll see one more later on, I suppose. But here I want to look at functions that can be computed in bounded time under a certain model of computation. Okay, and that fits into this model of, I guess I used some nomenclature. So this class of Boolean functions that we define down here is called a k combination of thresholded functions from G, this parameterized class. Okay, so the class I want to define is a k combination of threshold of functions from the class of polynomials, right? Polynomially parameterized functions for a certain value of k. So let me explain the model of computation. Here we're talking about how much time it takes to compute the value of a function, right? So we have our parameterized class Rd. These are the d real parameters, and let's say x is represented as a vector in Rn. And we're supposing that this is now a plus or minus 1 valued function. We're saying that this thing can be computed in no more than t steps of the following type, right? So we take as input a parameter and the x, and we return either plus or minus 1 after no more than t of these steps. And the steps we're allowed the model of computation, it costs 1 step to perform a single arithmetic operation, right? Addition, subtraction, multiplication, or division on real numbers. It costs 1 step to do a jump conditioned on any inequalities, any comparisons of real numbers, and 1 step to output minus 1 or 1. Okay, so if we have some program where a model of computation involves these sorts of, it costs 1 for each one of these operations, then we can count up how many operations it takes to compute the output for a given value of the input, I guess in the worst case over all input pairs A and X. And then in that case, it's easy to see that this function can be represented as a 2 to the t minus 2 combination of threshold of functions from the class of polynomials of bounded degree. Okay, we can't get, so any real valued functions we can compute here, real valued functions of A and X are polynomials, or ratios of polynomials, I guess, but their sign, when we consider the sign of those functions, they're polynomials. The degree is no more than 2 to the t. Okay, we can't increase the degree any more than doubling it as we go through, because all we can do is multiply, right? So each time we perform a multiply operation, we might be doubling the degree. And you can do a similar. You can argue that it's a vaguely 2 to the t combination of some Boolean. So you're combining up to 2 to the t Boolean functions, right? Just by considering the size of the execution tree here, right? As we look at all of these comparisons that we might make. Okay, so this is the kind of stereotypical example of k combinations of thresholded functions, in this case thresholded polynomials. And the result we're going to look at is for such classes. So before we go into that, let me tell you the punchline. We'll see that for this family, that the VC dimension of functions that can be computed in this way, so what's the class that I'm talking about here? It's the set of functions that map from Rn to plus minus 1 as the parameter A ranges over Rd. Okay? That's our parameterized family of plus minus 1 valued functions. And we're considering such a thing that can be computed in no more than t operations. For that thing, the VC dimension is no more than some constant times t, the number of operations, times d, the number of parameters. Okay, so we have this beautiful relationship between the computational cost of computing the value of a function, of a parameterized function of this kind, and the complexity in the sense of the VC dimension. So why is that true? Well, the argument is really quite geometric, where we work by bounding the growth function, and here, because we've got these nice, smoothly parameterized functions, we can think about bounding the growth function by looking in the parameter space at the cells that correspond to different sign assignments to some particular set of points. So remember the growth function we defined yesterday. If we have a set of m points, right, s of size m, the growth function the growth function at m is the maximum over all sets of m points of the cardinality of our class restricted to those points. Right? So what's the largest number of dichotomies of m points that we can achieve? So this is always smaller than 2 to the m, right? And we saw yesterday that it grows as 2 to the m up until m equals the VC dimension, and beyond that point it grows as m to the d, where d is the VC dimension, right? So exponentially, then polynomially. Okay, so in order to work out, I mean, we could work with the growth function or the VC dimension. We're going to work directly with the growth function. And we'll see this implies that the bound on VC dimension that I mentioned. Okay, so we're talking about a fixed Boolean function of k, threshold of parameterized functions, f1 to fk. So in order to show that this is not too big, we're going to fix a set S of size m, right? x1 through xm. And now we're going to think, okay, how many different dichotomies of those m points can we compute with our class, this fixed Boolean function of k parameterized functions? All right, well, in order to work out the number of dichotomies, let's look at these subsets of parameter space. Okay, so I here indexes one of these k different functions that we're combining. Right? We're computing k real-valued functions, then taking a fixed Boolean combination of them. So I indexes the k different functions. J indexes the m distinct points. So we're looking not in the input space, but in the parameter space. Okay? We're looking at where the function, the ith function at xj equals 0. So let's think about k equals 1 for now. Right? So we just have a single parameterized real-valued function. In parameter space, we'll have m of these sets, one for each point. And what does it correspond to? It corresponds to this, think of it as a manifold, right, where the value of that function passes through 0. Okay, if we want to get distinct sign assignments to these m points, and our functions are continuous, okay, then we have to pass through the set. If we want to change the assignment to x1, then we must necessarily go from f at x1 being minus 1, or being negative, to f at x1 being positive, right? If the sign is the same, we've got the same assignment. So we have to pass through this set where the function takes the 0 value. So these sets, and of course, if we're considering a Boolean combination of k of these things, well, we've got a bunch of these sets, right? K of them for k times m of them, right, for all ij pairs. So this carves our parameter space into a bunch of cells, right? Each one of the boundaries here, these sets, is the point where our function's value changes sign, right? And if we take Rd and throw out those manifolds, all right, then we're left with a bunch of cells. Within that cell, the sign assignment is constant. Okay, so all of these functions have a fixed sign. If we look at one of those cells carved out, I think I've got it's a way off. But so let's think of, here's one of the maybe this is a better example. Here's one of of those sets where a particular function, let's say f1, takes value 0 on x1, and maybe this is f1 taking value 0 on x2, and so on. Right, now within one of these cells, all of the fi's have to take the same sign on on all of the xj's, and so we can't get any more than one dichotomy within that cell. Okay, so these things carve our parameter space up into cells, which we can think of as the connected components of that set. And I've said this already, right? So if we think of all of the different dichotomies that are computed by our combination of functions, then and come up with a representative from our parameter space for each of the different dichotomies, then they have to lie in different connected components of this set. Well, not quite. It may be that some of the parameters that compute a certain dichotomy are computing it just because they lie right on one of those boundaries, one of those manifolds in parameter space. Okay, so it might be that we rely on having a 0 value of one of the functions in order to get a particular dichotomy. That's not a real issue. I mean, it's a technical point. We can always perturb the functions a little bit, and I'm going to skip over that. We can perturb the functions a little bit. We add in a little bit so that any time we have one of those, maybe there's, at this point here, we can compute a certain, in parameter space, we can compute a certain dichotomy that we can't compute in any of these cells. So fine, we can add a little something onto our functions to ensure that there are no such points that matter to us, right? So, this is a technical issue, and we can always get around it. So then we have this happy situation that for every dichotomy, there is a cell in parameter space here that gives us that dichotomy, right? And we can't change our dichotomy without moving from one cell to another. So now our problem of bounding the growth function is reduced to the problem of counting the number of these cells that we have in parameter space. Okay. Okay. So there's this nice theorem of Warren that says. So the application of this theorem is due to Goldberg and Jerem. A paper in 95. So there's a theorem due to Warren that says that if the intersections of the sets where these functions are zero are well behaved, you don't have any kind of degenerate behavior, and the precise definition is not important. I can tell you in a moment. Then the number of connected components, this notation means the number of connected components in the cells that we get when we throw away the zero sets is bounded by the number of connected components in various intersections of these zero sets. Okay, so in the linear case, right, that's a good example. If these FIs are always linear, okay, then the number of connected components here is either 1 or 0, right? If you're talking about linear subspaces now, right, you're intersecting these things. They either have a non-empty intersection, in which case it's a linear subspace, and there's only one connected component, or it's an empty intersection. Okay, so in the linear case, this is either 0 or 1, and we're doing some sort of a combinatorial count over subsets. Count the number of connected components, the number of cells in our parameter space that we get when we remove these zero sets, as long as we can get a handle on how many distinct connected components there are in the intersections of these various zero sets. Okay, so for linear functions, this is trivial. For polynomially parameterized functions, all right, this is something that has been studied. It's like the number of solution regions, right, to a bunch of polynomial inequalities. And this is what this is the theorem that we'll use. Okay, regular zero set intersections just means we don't have the zero sets touching in an unnatural way. So actually, this is not regular because we've got an intersection of kind of too many of these zero sets, right? It's a non-generic property. Generically, you always have this touching is non-generic, right? Generically, you always have regular zero set intersections, and so we can again perturb things. Another technical point, we can throw in some extra little offset here and not change anything by very much, and we've got that property satisfied. So let's sweep that under the carpet and forget it. And that's more sweeping under the carpet. Okay, so that's it, really. The growth function, we've seen that when we look at throwing away these zero sets that we get from our parameterized real-valued functions, when we throw away the zero sets, how many connected components are we left with? Well, that's an upper bound on the growth function. Okay. That thing through Warren's theorem is bounded by the sum over intersections of any size of the number of connected components in these intersections of the zero sets. And so if we have a bound on the number of connected components in the intersection of I zero sets, right, so bound on this thing, of size bi, then there are km choose I many subsets of size I, and we get a bound of this form, right? So everything reduces to being able to bound the number of connected components in the intersection of I zero sets of our parameterized functions. Well, this is something that, okay, and there's some terminology for that. You know, what did I mean by BI here? Sorry for that, but then there's theorem. So if we've got a function, a real valued function, so we're considering a class that's a k combination of thresholded functions from G, and G is a parameterized class that is twice differentiable in its first argument. All right, the twice differentiable is so that we can get away from these non-generic situations of, you know, touching zero sets. Then the growth function is bounded by this sum from 0 up to the size of the parameter space, the dimension of the parameter space. This m is the argument here of the growth function. K is the number of functions we're combining. It's a k combination. And b sub I is this bound on the number of connected components that we get when we intersect I zero sets of these functions. All right, so we've reduced the computation of the growth function to computing the number of simultaneous solutions, you know, not quite the number of connected components, but something like the number of simultaneous solutions to a system of equations involving these real value functions. Okay, and that's something that people have studied for centuries, I guess. So, you know, there's this.
Hi.
Yeah.
Just had a question.
Yeah.
So I'm having a tough time visualizing the last slide. Is it possible to give like a visual, I guess, a picture of all the interpretations?
Sure. So this is probably the best. So what you should think about is, here we're looking in parameter space, right? So we have our D parameters. D is 2 here, right? We have 2 parameters, and we have, let's think of, we're taking a k combination, think of k as 1. Okay, so we're just considering a thresholded parameterized real value function. We have 2 parameters, a1 and a2. Okay, and now we've drawn lines here to represent the zero sets, which is where our function f evaluated at a, comma x1 equals 0. This is the zero set for x1. So at this point, our function changes sign on x1. To this side, maybe our function is positive on x1. To this side, it's negative on x1. Okay? Here's a line for x2. Right? To this side, it's positive for x2. To this side, it's negative for x2. So, you know, for this parameter, for a parameter value in here, this value of a1 and a2, okay, we're negative for x1 and we're positive for x2. Okay, so you know, in there and you know, these lines are for other points. So here's x3 and here's x4. Okay, so as we move from here where we have a fixed sign, our function has a fixed sign for all of those points. As we move across this boundary, okay, x4's the value of f on x4 changes as the parameter moves from here to here. All right. So what we're doing is counting up the number of these cells. Okay, the growth function is the number of distinct dichotomies we can get on these 1, 2, 3, 4 points. The 4 points that correspond to these boundaries. And we're getting an upper bound on that by counting up the number of distinct cells in here. Okay, the way we compute this number of distinct cells is by counting up the number of connected components in intersections of the zero sets. So Warren's theorem tells us that if we want to count these cells, then we can relate that number to, we can get an upper bound on that number in terms of the number of connected components in intersections of the zero sets. So in this case, right, what's the largest? So I guess there are no points in the intersection of 3 of these zero sets, right? So in that notation I described earlier, B1, right, how many connected components in the intersection of 1 zero set? Well, it's always 1 here, right? At least as I've labelled these things, there's just 1 connected component for each zero set. Okay, B2 is the number of connected components in an intersection of 2 zero sets. Okay, and in some cases, so this zero set and this zero set have an intersection of those 2 points. So the number of connected components is 2.
right? So, and I don't think there's anything bigger, is there? Right, so B2 here is 2, right? B3 is 0. There are no non-empty intersections of 3 zero sets. Okay, so Warren's theorem tells us that to count the number of these components, we can count the number of zero set intersections, and then counting the number of zero set intersections is something like counting the number of simultaneous solutions of a collection of equations. So is that clear?
Yeah, thanks.
Okay, so for particular parameterized functions, like bounded degree polynomials, all right, there are classical results about the number of simultaneous solutions of such things, or the number of connected components of the solutions of such things, and bi for I up to D, this should say, has an upper bound like L to the D. What is L? L is the degree of the polynomial. D is the number of parameters. And so, as a corollary of this result, and it's 0 for I bigger than D. As a corollary of this result, we can plug that in to this previous bound on the growth function, and we get that the growth function looks like m is this argument, the number of points, k is the number of polynomials that are involved in our that we're combining somehow, L is the degree of them, and D is the number of parameters. Okay, and so just comparing this to 2 to the D, we get that the BC dimension is no more than D times log k times L. All right. Okay, why do we care so much about polynomials? Well, that was the stereotypical example. That was this really nice the case of bounded computation functions, right? So if we take this model of computation to compute some function from our parameterized class, we can take no more than t steps of these kinds of operations. Then we've seen that means we're taking a k combination for k like 2 to the t, right? Of polynomials of degree no more than 2 to the t. Okay? And so when we plug all that in to our result for polynomials, right, anything we can compute in t of these computational operations has VC dimension no more than the time it takes to compute it times the number of parameters, modulo a small positive. Yeah, so I think this is a very nice relationship between the computational complexity of evaluating a function and the statistical complexity of the class of plus minus 1 valued functions that we have. I'll probably pause there for questions.
Peter, I guess I had one question. So would you use? So let's say if I have a real problem, would I use this as a test before I begin on my data set to give me an idea of how would I use this?
Okay, so I mean this is a result that tells you that this is a very easy to apply tool to get a bound on the VC dimension of a parameterized class. Okay, so you can easily get order of magnitude kind of results out of this for an enormous variety of VC classes where with a more refined argument in some cases you can do better than this, but it's often really very simple to get an estimate of this kind for a class. So for instance, I'll give an example in the research talk this evening in looking at the consistency of AdaBoost. An essential ingredient there is that the basis functions that we use have bounded complexity in this sense, right? So if we want to know that there we're not so concerned. I mean, here in the minimax setting, the VC dimension gives us these finite sample results, these optimal finite sample results, modulo constant. for the performance, some bound on risk, what I call the minimax estimation error yesterday. There, we're concerned not with finite sample results, but just consistency in what I'll present later on. But it's still essential to have finiteness of the VC dimension to be able to do that. And this is a very, very large class, very, very large family of function classes for which we could prove such a thing. So it's a general and very easy to apply tool. Any other questions? Okay, so there are extensions of this that you can consider. You can add in operations to the model of computation. So when we looked at just these usual arithmetic operations on the real numbers, we can add in other functions and say that they cost us just one step. And come up with similar kinds of estimates. And things with the exponential function, things get a little worse. It turns out you can. So we know, for instance, we couldn't add in the sinusoid here and get a result of this form, right? But it turns out that anything that satisfies a first-order differential equation, even non-linear, first order, will lead to something like this. But this is a sufficient condition to get some nice relationship between the number of parameters in the VC dimension, and I guess there's still a lot that we don't know about to what extent we can extend these sorts of ideas. But this, of course, means that for the usual sigmoid function, sigmoid neural nets, we can get some estimate on the complexity of that class. Okay, and so these are the I guess applying that, if we consider a neural net with the usual logistic nonlinearity, 1 over 1 plus sigma minus x, then we get an order of number of parameters to the power 4 as an upper bound. We know that if the nonlinearity is piecewise polynomial, we can use these ideas in a less direct way to get that it's essentially order of the number of parameters. Okay, so let me again, I should probably pause there before we move on to large margin classifiers. So one of the things, these results for neural nets, I think it's very nice that we can get such estimates, it's sometimes essential in that case to be working with the VC dimension. But for neural nets themselves, the typical optimization that's performed is of a smooth criterion. You choose a real value function to optimize some smooth criterion like squared error, and in that case, the minimax setting is too harsh, right? Because our optimization is not good enough to really run into the sorts of troubles that the minimax lower bounds would predict we'd run into. Okay, so this is one advantage of the large margin kind of formulation that I'm going to tell you about next. I guess the disadvantage is that we're really not able to exploit the full power of the class of functions that we're talking about in that case. All right, are there any other questions before we move on to large margin? Okay, so in the next part, we'll have a break in 10 slides time. In the next part, I want to tell you about some results for large margin classifiers. First of all, we'll look at this large family of classifiers. I guess you've seen already in some of the earlier talks specific examples and this viewpoint of optimizing a smooth criterion as viewed as a large margin classifier. So the things that I want to concentrate on here are how we can quantify the performance of these things, and in particular, we're going from an empirical risk kind of criterion, which seems rather close to what we care about, right? We really want to find a classifier that minimizes risk, that has small probability of misclassification. Well, when we move to a large margin classifier, we're minimizing some other kind of a quantity, a smooth quantity. It's not the right thing, right? So, how are those two related? Are we does it make sense to minimize this other criterion? And for what convex, what smooth criteria does it indeed make sense? So we'll look at that. We'll look at how minimizing, one of these surrogate cost functions leads to a different kind of decomposition into approximation and estimation errors. Right back at the start of these lectures, I've told you about these ideas of approximation, the approximation properties of a class and the statistical or estimation properties, and how we need to trade those off. Well, here the decomposition is a little different because the approximation properties that are relevant, it's not what's the best, what's the minimal misclassification probability I can get using thresholds of functions from my class, right? It's the relevant approximation property is in terms of this smooth criterion that we work with. So I want to look a little bit at that, and then finally I'll say just a few words about how the large margin kind of criteria are related to estimation of probability models. So estimating the conditional probability that y equals +1 given a certain x. Right? In some cases they are related, in other cases they're not, and I will look into that. Okay, so just to review, what we're hoping to do is use our data x1, y1 through xn, yn to choose a function f that has small risk. So the expectation of let's say the 0, 1 loss should be small. That's a natural approach to minimize the empirical risk, right? R hat of f, which is the sample average of the loss on our data. But in many cases, this is computationally intractable. And I guess I haven't presented any formal results here, but for things like the neural net classes that we presented, this optimization problem is intractable, except in very special cases. For decision trees, it's intractable. For convex combinations of any interesting class, it's intractable. Right, so it's a nice aim, but it's not something that we want to be able to compute quickly. So, I guess it really depends on the audience how much that concerns you. This is mostly a computer science audience, so I probably don't need to carry on about this. But as soon as in front of a statistical audience, they say, why worry? It's just a background issue, I think, sociological issue. Anyway, I think with large margin classifiers, the general approach here, you can view a big family of these successful pattern classification techniques as working by replacing this discrete loss with some sort of a convex surrogate, right? So that we go away from this, what has a combinatorial flavor, this hard optimization problem of minimizing the indicator for making a mistake here, with some convex function. So that this optimization becomes, if f is linearly parameterized, becomes a convex optimization, something that we know how to solve efficiently, efficiently in a formal sense. Okay, so just to introduce some notation here. So we have if fn is this function that we choose given the data, and we're interested in the risk. But instead of optimizing the empirical version of that I showed you on the last slide, we consider what I'll call the margin. I guess you've seen this already. So y here is plus minus 1, and fn of x is a real valued function, and we'd like the sign of that thing to be correct. Okay, so we'd like the sign of fn of x to be the same as y with high probability. Okay, so our risk now, I've slightly generalized the 0, 1 loss, right, by saying not just the indicator of y being not equal to fn of x, but for a real value of fn of x, I'm concerned with the sign. So now, when we look at the product here, y is plus minus 1, fn should have the same sign. This thing should be positive, right, for fn to classify y correctly. But instead of just worrying about it being positive, we could define some cost function that we evaluate at these margins, right? Let's say it's a non-negative function, right? And then define the phi risk of a particular f, real valued f, as the expectation of phi of y times f of x. Okay, so if this thing is, think of it as some decreasing function. Actually, before the board was erased, there was a picture of one over there. We'll see some pictures in a moment. Right, and we're interested in the expectation of this decreasing function being small. So this is pushing y times f of x to be big. Yeah. So the broad approach here is, once we have this surrogate cost function, we use the notation R sub phi for risk involving this surrogate phi. Once we have this surrogate cost function, we choose a function from our class to minimize the phi risk, to get this value as small as possible. And for instance, we might use our xy pairs and minimize empirical phi risk. Right? The sample average of this thing, which we denote R hat sub phi of f, or some regularized version of that, the usual kinds of things. So there's a big family of pattern classification algorithms, very successful pattern classification algorithms, that can be viewed in this kind of a way. Right? We can view, for instance, AdaBoost in this sort of a way, right? Which I guess would be the origin of the picture up here. Right? We can think of our class, the class f from which these real valued functions come, right? These things, as the span of some set of classifiers that we'll see necessarily have finite BC dimension. Okay, the cost function in the case of AdaBoost is the decreasing exponential, right? So if y times f of x, as y times f of x gets bigger, this thing gets exponentially smaller. And AdaBoost, the algorithm works in a particular way. You've seen this already, right? It's doing some sort of greedy basis selection and then line search. So you choose a function to add into your combination. You're working with linear combinations of these classifiers, and at each step you're adding in a function in a way that greedily minimizes the sample average of this exponential cost. And then once you've picked that function, you can think of it as doing a line search in that direction. Right? So we're looking across this function space, span G, and moving always in the axis, in parallel directions, where sort of think of it as axes, I guess. So we're moving always in the directions of functions in G, right? So we're just picking a single function and then moving, doing a line search in that direction to go to the minimum of the sample average of phi of y. So that's AdaBoost. Support vector machines can be viewed in exactly the same way. So for instance, what have I got? This is not a normal hinge loss. I've squared it here. Whatever, right? So this is with the 2 norm soft margin. Okay, then the cost function is the hinge loss squared, right? And the class of functions that we're choosing things from is, I say a ball. I mean, it comes from a reproducing kernel Hilbert space of some kind. And the algorithm works by minimizing the sample average of the phi risk, right? The empirical phi risk plus the regularization term. Right? There's this penalty involving the RKHS norm of the function f squared. Okay, so that's support vector machines, and of course we could choose all sorts of different cost functions here and have many different varieties of support vector machines. And there are lots of other variants. Neural net classifiers are actually working in exactly exactly this way also. We have a certain class of functions, it's non-linearly parameterized, right, here, and the phi risk we're working with there is typically some quadratic kind of a thing. We could add some other cost function to support vector machines or to boosting. You can also view logistic regression in this sort of a way, right, where you're wanting to fit, come up with a maximum likelihood fit to a certain probability model. You can view that as minimizing one of these cost functions also. And so here's a picture, the one that I promised you. And this is showing, I've rescaled some of these, probably hard to read. This is on the x-axis here is the margin, right, y times f of x, and on the y-axis the cost function. This is the normal risk, the 0-1 risk, right? So when the margin is positive, we have zero, a zero cost. When the margin is negative, we have a +1 cost. So our loss function is just this indicator of misclassifying with the sign of f of x. The green line here is the hinge loss, the usual loss used with SVMs. What else? When we square that, we get this brown line. Okay, there's an exponential in there somewhere, the red one, right, used by AdaBoost. And there's another one, logistic is the one that I've scaled here, right? You can see all of these things we can think of as, there are a few things to notice, we can think of them as upper bounds on this quantity. But viewing them just in that way, unless we can get a nice small value of our upper bound, it might not be very productive to view them as upper bounds. Right? Just to say, oh, this is why the algorithm is working, it's because of minimizing upper bound. So we'll say a little bit more about that later, but we can view them in that way. I guess one thing to notice here is that all these things are convex functions. Yeah.
Here you say that the truncated quadratic.
Yeah.
In the previous slide, you have the least squared support vector machine. Actually, that's a
oh yeah, that's not truncated. This one. I guess I was talking about this one. Yep. This is the one that I plotted up there in red. I guess it's the hinge loss squared. But in LSS VMs, yeah, they're not truncated.
Yeah.
The reason, I mean, that's a computational thing, right? In least squared support vector machines, people want to work in the primal and have a very standard, matrix inversion kind of problem to solve there, right? Whereas with this truncated form, you don't have that. You have a QP here. So the computational complexity of solving the optimization problem is simpler in the primal at least, is simpler in this case than in that case. Yeah. So I mean, it does. I agree. It looks strange to use the quadratic, which gives you an increasing penalty out here, right? That seems like a strange thing from the approximation theoretic point of view. You only lose by doing that, right? It can't help you. On the other hand, there is a computational advantage to working with the quadratic cost. If you're working in the primal, so if you have, for instance, a linear kernel that's not too high dimensional, then this is just a simple matrix inversion when you use that function rather than a full QP. But it is an approximation. It is a lose when you look at it. It's a bad thing to do from the point of view of the approximation theoretic properties. That's right. Okay, so and for all of these, there are the algorithms are all different. There are QPs. There are just least squares problems. The AdaBoost is a kind of forward stage-wise optimization. All these things we can come up with some sort of guarantee of how good our solution will be after a particular number of iterations of the algorithm, a particular amount of computation, precisely because we have a convex criterion here, right? So we're going from this nasty non-convex thing to a convex criterion, and from the computational point of view, that's a good thing. But and this is the point where I'll pause. This really raises a whole bunch of questions about this sort of approach, where we're just throwing out the discrete cost function and putting in there a nice convex one because of the computational convenience that we get out of that. Okay, and so that raises questions. Is that a sensible thing to do? Does minimization of this convex criterion, suppose we could minimize the expectation of phi of y times f of x, right? Minimize the phi risk. Does that lead to minimization of the risk? Right? And for what cost functions does it lead to minimization of the risk? And so we'll have a look at that. We could ask this question of, can we hope to develop a universally consistent method using this sort of approach of minimizing phi risk? So by that I mean universally consistent. I mean, can we hope to develop a method that for which whatever the probability distribution will come up asymptotically as the amount of data gets large, will come up with the right classifier, the optimal classifier. Is that the case? Is that possible at all with a particular convex cost function? And in fact, we can refine all of these questions. We'll see that there's a relationship between the risk and the phi risk, right? That those two can be related. So we'll have a look at that. All right. So that's probably a good point to pause. Are there any questions? No, I just had the time wrong. You're right, fine. I can talk for another 15 minutes. I'm sorry, I had in mind that it was at 2:30. Okay, so we'll keep going. Okay, so let's look at that. I have to find another natural function. Right, so I guess there's been a whole lot of work on these sorts of questions. People who have examined particular algorithms, split vector machines, and regularized boosting, regularized versions of AdaBoost, for instance, in various settings. The two, I guess, papers that are at the heart of what I'm going to tell you about is a paper by Tom Zhang on regularized boosting. It also has some of this regularized boosting in SVMs. It also has some of these ideas of finding an interpretation of minimization of the phi risk as fitting a probability model. So I'll say a little bit about that. And also this paper where we look at characterizing, this is with Mike Jordan and John McCord, where we look at characterizing the kinds of loss functions for which minimization of the expectation, minimization of the phi risk corresponds to or leads to minimization of the risk. Okay, so that's the first thing I want to look at, is this issue of relating excess risk to excess phi risk. So let me just fix some notation to get started. So we've seen the risk. We're talking about a real valued function, right? The risk of f is the probability that the threshold of value of f is different from y. Okay, we'll denote by r star the Bayes risk. Okay, so this is the infimum. The infimum here is overall measurable function. So this is the best we could do if we had complete knowledge of the probability distribution, right? We just choose our classifier here to label it as +1 if the conditional probability that y equals 1 is greater than a half, and -1 otherwise. right? We get that's the optimal risk if we knew the probability distribution. So we call that R star, and we define the analogous quantities for this cost function phi. All right, R phi of f we've seen as the expectation of phi evaluated at y times f of x, and R phi star, right, is the analogous quantity to the Bayes risk. It's the in theorem overall measurable functions f of the phi risk. Okay, so again, it's the smallest risk that we can achieve if we knew the probability distribution completely. Okay, some other notation that I'll be using. We have the conditional probability that y equals 1 given a particular value of x. All right, we'll call that eta of x. And that defines, well, I've already mentioned that defines an optimal classifier, right? The Bayes risk is achieved by the function that returns +1 if eta of x is bigger than a half, and -1 if eta of x is less than a half. Okay? It turns out it also defines the optimal real valued function for minimizing the phi risk. I mean, it's obvious, but you can write that down explicitly, and we'll do that a little later. All right, so a crucial decomposition in what we do is to rewrite this expectation as the expectation of a conditional expectation. Okay, so we're thinking of, right, so this expectation here, we can write as the expectation over x of the conditional expectation of phi of y times f of x given x. Okay? And then it's this conditional expectation that we're going to focus on. So equivalently, that's like thinking, all right, we need to minimize the expectation of phi of y times f of x. What happens if we fix a single x? Right? Or equivalently, what if our domain was of size 1? There's only one x. And we just have some distribution on y. Right? There's a certain probability that y equals +1 and -1. So let's look at that and at that conditional expectation. So we're fixing a certain value of x and looking at this conditional expectation. Well, we can rewrite that, right, in terms of the conditional probability as the probability that y equals 1 times the value of this thing when y equals 1 plus the probability that y equals -1 times the value of this thing when y equals -1. Right, and that's a crucial quantity. So, we'll see that to minimize the phi risk, we can come up with a measurable function that point-wise minimizes this thing. Okay, so all right, so some more notation that's going to be important in what we do here. The optimal conditional phi risk for a given value of the conditional probability. Okay, so we're looking at this conditional expectation and saying, now, suppose we know we fix an x and it has a certain value of this conditional probability. Let's call it eta. So what's the value of f of x that we should choose? For that x, what should the value of our function be so as to minimize this conditional expectation? Okay, so we fix that conditional probability and then we minimize over all values that our function might take here, right? The convex combination of phi of alpha and phi of minus alpha, weighted according to the probability that y equals 1 and the probability that y equals -1. Okay, so this is the smallest value that we can get for this conditional expectation. Right? And then we can express the optimal phi risk as the expectation of this thing. Okay, where we're replacing eta here, some constant by the value at a random x. Okay, so if this infimum can be realized, then we can the corresponding alpha for a given x gives us the function that achieves the phi risk r phi star, the optimal phi risk. Okay, so this is an important quantity in what we're doing here. And I need one more definition. Well, okay, let me do a picture first. We need one more definition. Concentrate on the left diagram here. All right, so here we've got, this is the truncated quadratic criterion. Right, so it's 1 minus alpha squared to the left of 1 and 0 to the right of 1. Right. So that's phi of alpha. When we consider the flip side, right, when we take the reflection through the y-axis, we get phi of minus alpha. That's this blue line. Okay, and the thing we're considering in this conditional expectation is some combination, or we can look at it down here, some combination of phi of alpha and phi of minus alpha, all right, weighted by the probability that y equals 1. Okay, so the red curve, for instance, is when eta is 0.7. Okay, so it's 0.7 times the black curve plus 0.3 times the blue curve, and we get this quadratic thing. Right. And similarly, the green is when eta is 0.3, so it's 0.3 times the black, 0.7 times the blue. Yeah. And then we're looking at h is what's the value of the minimizer. What's the minimal value of this thing for a given value of eta. So here's a particular value where here's the curve where eta is 0.7. The minimizer is here, right? That's the minimal value there. If we look at 0.7, this is the minimal value over here, right? If we took a 50-50 combination of these two, when eta is a half, we'd get a minimum here, and the minimal value would be 1. Right? That corresponds to that point. And as eta moves to more heavily weight this one, right? This h of eta moves down. Okay, and you could do this analytically. The shape is always the same. H is always convex because it's an infimum. Convex in eta because it's a minimum. Concave in eta because it's a minimum over concave functions, linear functions of eta. Right? So it always has this entropy-like shape. As the conditional probability moves from 0 to 1, we get this thing going up and down again. It's always maximized at a half. Okay, and I've also drawn. Is there a question? Yeah.
Well, this definition depends on the function f.
On the function f. Oh, right. So what I'm getting to here is how we can relate the risk to the phi risk, right? And what we're trying to do is say in the case where so I guess the first step is to ask what's a suitable convex cost function phi, yeah, and we're minimizing the expectation of phi of y times f of x. We're minimizing this phi risk. Is that a sensible thing to do? So suppose we knew the probability distribution, right? Suppose we could come up with an f that optimized the expectation of phi of y times f of x. Actually gave the minimal value. Would that f work, right? Or being a little more cautious, suppose we had a sequence of x for which that the sequence of phi risks converge to the optimal value. Would we then get the risk converging to the optimal value? Right, this is what we're shooting for. We'd like phi to be appropriate in that sense. Minimization of phi risk to be an appropriate thing to do in that sense. Okay, so the f at this point has gone away. All right, we're thinking now of f of x as being optimized separately, pointwise at each x. So it'll come back in a moment. Right? We'll be concerned later with worrying about optimization over a fixed class, where then we have additional issues to concern us. Right? We have to worry about an approximation error that arises. If we're choosing f from some restricted class, then we might not be able to minimize the phi risk. This is saying even in the population case, even when we have complete knowledge of the distribution, does it make sense to minimize the phi risk? Does that lead to a minimum of the risk? Yeah. So that's what we're shooting for. And at this point, I'm just wanting to introduce some notation to get us to that endpoint. Okay, so this is the optimal value for a particular value of the conditional probability. So this is focusing on a single x, right? And you know, we're not worrying about a function x. We're worrying just about the optimal value that we could have at that one fixed x that has a certain value of the conditional probability, right? What's the smallest value of this conditional phi risk? That's this function h of eta. So as the conditional probability varies between 0 and 1, so the probability that y equals 1 given our one fixed x varies between 0 and 1. The value that we see when we optimize the conditional expectation of phi of y times f of x is going to vary like this. Okay, and in this case, for the quadratic guy, the optimal value is just some simple linear function of the conditional probability. You know, it's easy to verify that. Okay, so I want to give you one more definition to think about at the break. So this is the optimal conditional phi risk. What happens if, for a particular value, again, focus on one value of x, what happens if, instead of optimizing over all values that our function f of x might take, we're forced to optimize with the constraint that f of x has the wrong sign. Okay? So suppose that we fix our x, the conditional probability that y equals 1 is greater than a half. Right? Well, f of x should be positive if we want to classify that correctly. That point correctly. Okay? The Bayes classifier will say +1 if the conditional probability is greater than a half. Right? Suppose we're forced to make a mistake on that point. Suppose we're forced to have the sign of alpha different from the sign of eta minus a half. Okay, so let's do the minimization subject to that constraint that we make a mistake at this one point we're focusing on. We'll call that h minus of eta. Okay? Now certainly, this is a constrained optimization. It's got to be no better than the unconstrained optimization. Alright? But we should hope, if minimizing phi risk makes sense, right, we should hope that being allowed to get the sign right will let you do strictly better than not being allowed to get the sign right. Otherwise, you could optimize and get the sign wrong, and then we're in trouble for classification. Right? So that's the definition of classification calibrated. It's just worrying about what happens point-wise. Right? If we think about a single x and a single value of the conditional probability, h of eta is the value we get when we minimize the conditional expectation of phi of y times, you know, this f of x. H minus of eta is the value we get when we minimize the same thing, subject to the constraint that the sign of f is wrong at that x. Right? It's different from the Bayes classifier. And we want this to be strictly smaller than that. Okay? If it's not, then I can easily provide a counterexample to the claim that minimizing phi risk is a good idea. Right? I give you a single x and a value of eta for which this thing is the same as that thing, and then you can minimize it and get the wrong sign. Right? And so you can't possibly minimize the risk with such an approach. Right? So this is clearly a necessary condition for minimization of phi risk to be a sensible thing. So we say that phi is classification calibrated if whenever the conditional probability is not equal to a half, the sign constrained case is worse, strictly worse than the unconstrained case. Okay, and of course, if the conditional probability is equal to a half, well, we really don't care, right? Because you can predict anything you like, and you're doing just as well as the Bayes rule. Okay, so that's obviously a necessary condition. We'll see after the break that it's also sufficient. It turns out worrying just about what happens point-wise is enough. Right? That under this condition, optimization of the phi risk corresponds to optimization of the risk in the population case. So, are there any questions? Now we've gone over time. It was perfect if we were going to finish it up.